Hi, welcome back to educator.com. Today we're going to talk about exponential functions. Previously, we've spent quite a while looking at functions that are based around a variable raised to a number, things like x squared or x to the 47, right? This is basically the idea of all those polynomials we worked with for so long. But what if we took that idea and we flipped it? We could consider functions that are a number raised to a variable, things like 2 to the x or 47 to the t, where we've got some base number that has a variable as its exponent. We call functions of this form exponential functions, and we'll explore them in this lesson. Now, make sure that you've got a strong grasp on how exponents work before watching this. If you need a refresher on how exponents work, check out the previous lesson, Understanding Exponents, to get a good grounding in how exponents work. All right, an exponential function is a function of the form f of x equals a raised to the x, where x is any real number and a is a real number such that a is not equal to 1 and a is greater than 0. We call a the base. The base is just the name for the thing that's being raised to some exponent. So whatever is being exponentiated, whatever is going through this process of having an exponent, that is called the base because, it forms the base because it's below the exponent. We might wonder, why are all these restrictions on what a can be? Well, there's good reasons for each one. If a equals 1, we just have this boring constant function because we'd have 1 to the x, which is just equal to, not equal to x, it's just equal to 1 all the time. So something that's just equal to 1 all the time, not really interesting, and it's not really going to be an exponential function, so you're not going to consider that case. If a equals 0, the function wouldn't be defined for negative values of x, right? If we tried to consider what is 0 to the negative 1, well then we'd get 1 over 0, but we can't do that. We can't divide by 0, so that's not allowed. So that means a equals 0. Once again, not going to allow that one. And if we had a is less than 0, then the function wouldn't be defined for various x values like x to the 1/2. For example, if we had negative 4 and we raised that to the 1/2, well, we know raising to the 1/2 is the same thing as taking the square root. So square root of negative 4, hey, we can't take the square root of a negative because that produces imaginary numbers, and we're only dealing with real numbers. We're not dealing with complex numbers right now, so we're going to have to ban anything that's less than 0. And that's why we've got these restrictions on our base has to be greater than 0 and is not allowed to be 1, because otherwise things kind of break down for the exponential function. All right, notice that from the previous lesson we can compute the value of a given base raised to any exponent. We know how exponents work when they're a little more complex, not complex numbers, but just more interesting. And so we can raise things like 4 to the 3/2 equals square root of 4 to the 3, which would be equal to square root of 4 is 2, 2 cubed, 2 times 2 times 2 gives us 8. Great. If we had 7 to the negative half, well, negative 2, sorry, then that would become 1/7 because we've got the negative, so the negative flips it to 1/7 squared. So 1 squared is 1, 7 squared is 49. We get 1 over 49. So we can do these things that are a little more difficult than just straight positive integer. But we might still find some calculations difficult. Like, right, if we had 1.7 to the 6.2, that'd probably be pretty hard to do. Or the square root of 2 to the pi, these would be really difficult for us to do. So how do we do them? In practice, we just find these expressions, or a very good approximation, by using a calculator. We can wind up getting as many digits in our decimal expansion as we want. We can just find as many as we need for whatever our application is, whatever the problem asks for, by just using a calculator. Any scientific or graphing calculator can do these sorts of calculations. There will be some little button that will say x to the y, or some sort of blank to the blank, some way to raise to some unthing. They also to something random. They might have a caret, which says, if I have 3 caret 6, whoops, not with an A, I accidentally drew that in. If I had 3 caret, oh my goodness, I drew it in again. 3 caret 6, then that would be equivalent to us saying 3 to the 6, the caret saying go up. So the calculator would interpret 3 caret 6 as 3 to the 6. So there's various ways, depending on if you're using a scientific calculator, if you're using a graphing calculator, to put these things into a calculator and get a number out. So we were able to figure these things out just by being able to say, use a calculator. Now, from a mathematical point of view, that's a terrible statement. We don't want to say, hey, we can deal with this because we've got calculators, because how did you figure it out before you had calculators, right? Calculators didn't just spawn into existence and give us the answers. We can't rely on our calculators to do our thinking for us. We have to be able to understand what's going on, otherwise we don't really have a clue how it works. But as you'll see as you get into more advanced math classes, there are methods to figure out these values. There are ways to do this by hand because there's various algorithms that give us step-by-step ways to get a few decimals at a time. Now, doing it by hand, long, slow, tedious, it'd be hard to get this sort of stuff just because it'd be so much calculation to do. We could do it, but you know, that's what calculators are for. They're to do lots of calculations very quickly. They're to help us get through tedious arithmetic. So since these sorts of calculations, they take all of this arithmetic, we designed calculators that can do this method for us. And that's why we can appeal to a calculator. Not because the calculator knows more than us, but because at some point humans figured out a method to get as many decimals as we wanted to, and then we just built a machine that's able to crunch through it quickly and rapidly so we can get to the thing that we want to look at, which is more interesting in using this. So the calculator is a tool, but it's important to realize that we're not just relying on it because, you know, it has the knowledge. We're relying on it because at some point we built it and put these methods into it. And if you keep going in mathematics, you'll eventually see, oh, these are where the methods come from. Some pretty interesting stuff in calculus. All right. Now, if we can evaluate at any place, if we can compute what these values of exponential functions are, then we can make a graph, right? Because we can plot as many points as we want, and we can draw a smooth curve. So let's look at some graphs where the base is greater than 1. If we have 2 to the x, that would be the one in red, 5 to the x, that's the one in blue, and 10 to the x, that's the one in green. Now notice, 2 to the x, 5 to the x, 10 to the x, all of these wind up going through 1 right here, because what they're happening there is it's 2 to the 0, 5 to the 0, 10 to the 0, anything raised to the 0, they all wind up being 1. Remember, that's one of the basic properties of exponents. If you raise something to the 0, it just becomes 1. So that's why we see all of them going through the same point. And notice that they get very large very quickly. By the time, you know, 2 is to the 4th, it's already off, and 10 is off by the time it gets to the 1. So 10 to the x grows very quickly because it's multiplying by 10 each step it goes forward. Notice also, as we go far to the left, it shrinks very quickly. Let's consider 10 to the negative 3. 10 to the negative 3 would be the same thing as 1 over 10 to the 3, which would be 1 over 1,000, right? So 1 over 1,000, that's why we wind up seeing this green line is so darn low. It looks like it's almost touching the x-axis. It isn't quite. There's this thin sliver between it, but it's being crushed down very, very quickly because of this negative exponent effect where it gets flipped over and then it, you know, has a really, really large denominator very quickly. So we see as we go to the left side, as we go to the left with these things, it will crush down to 0, and as we go to the right, it becomes very, very big. We can change the viewing window so we can get a sense for just how darn big these things get. And look at how big. We've gotten up to the size of 1,000 by the time we're only out to 10. And that's on 2 to the x. If we look at 10 to the x, 10 to the x has already hit 1,000 at 10 to the 3rd, right? At x equals 3, it's managed to hit 1,000 as its height. So this stuff grows really quickly. This idea of massive growth is so central to the idea of exponential functions, we're going to have a story. So there's this story that often gets told with exponential functions because it's a great idea to bring home, it's this great way to bring home just how big this stuff gets. So let's check it out. All right. Long ago in a far-off land, there was a mathematician who invented the game of chess. The king of the land loved the game of chess so much he offered the mathematician any reward that the mathematician desired. The mathematician was clever and told the king, "Humbly, your highness, I thank you. All I ask for is a meager gift of rice given day by day on a chessboard. Tomorrow I would like a single grain of rice given on the first square. On the next day, 2 grains of rice given on the second square. Then on the following day, the 3rd day, 4 grains of rice, and so on and so forth, doubling the amount every day until all 64 squares are filled." So the mathematician is asking for first square, doubled, 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 doubled. The mathematician drew the king a diagram to help make his request clear. On the first day of his gift, he would wind up having 1 grain of rice on the first square, so 1 grain of rice. On the second day, there'd be a total of 2 grains of rice. 1 times 2 becomes 2. On the 3rd day, there would be a total of 4 grains of rice. 2 times 2 becomes 4. On the next day, there will be 8. 4 times 2 becomes 8, and then 16, and then 32, and so on, and so on, and so on, going all the way out to the 64-day, doubling each time we go forward a square on the board. The king was delighted by the humble request and agreed to it immediately. Grains of rice? I mean, come on. You can get a lot of grains of rice on a single chessboard. It'll be very easy, he thought. He ordered that the mathematician would have his daily reward of rice delivered from the royal treasury every day. A week later, the king marveled at how the mathematician had squandered his reward. After all, he only had to send him 2 to the 6th equals 64 grains of rice that day. Notice, on the 7th day, so the 7th day, we're at 2 to the 6th. So let's see why that is. On the first day, we have 1 grain. On the second day, we have 2 grains. On the third day, we have 4 grains. On the fourth day, we have 8 grains. The fifth day, we have 16 grains. The sixth day, we have 32 grains. And thus on the seventh day, we have 64 grains. So notice, we can express this as 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, and then finally 2 to the 6th on the 7th day. Why is this? Because on the very first day, he just got 1 grain. Every following day, it multiplies by 2. It doubles. So that means we hit it by multiplying it by 2. So we count all of the days after the first day, which is why on the 7th day, we see an exponent of 6. So in general, it's going to be 2 to the number day minus 1. We'll subtract 1 to figure out grains on some number day. So now we've got an idea of how we can calculate this pretty quickly and be able to get these things figured out. Another week later, on the 14th day, the king sent him 2 to the 13th, remember, because it's 14th day, so we go back 1 because it's been multiplied 13 times, 2 to the 13th grains of rice, which is 8,192 grains, and 8,192 grains is just about a very large bowl of rice. The king was still amazed at the fantastic deal he was getting, but he was glad that the mathematician was at least seeing some small reward. He loved the game of chess after all, and if he wound up feeding the mathematician for a year, hey, that's great. It seems like a wonderful deal. He was willing to give him palaces, jewels, massive amounts of money. He can give him a little bit of rice for the great game of chess. At the end of the third week, on the 21st day, the king had to send the mathematician a full bag of rice, because in the kingdom, a full bag of rice contained precisely 1 million grains. So on the 21st day, we have 2 to the 20th grains of rice, which winds up being 1,048,576 grains. So we see here, after we jump these first 6 digits, we have 1 million plus grains of rice. So he's managed to get 1 million grains of rice, which is 1 bag of rice, plus an extra 48,000 and change in grains. So perhaps the mathematician was not as foolish as the king had first thought. At the end of the 4th week, the king's starting to get worried. On the 28th day, he has to send him more than 134 bags of rice, because 2 to the 27th is more than 134 million grains of rice. So we're starting to get to some pretty large amounts here. Now, the royal treasury has a lot of rice. He's not worried, it's got hundreds of thousands of bags of rice, so he's not too worried about it, but he sees that this is starting to grow quite a bit. At that moment, the royal accountant bursts into the throne room and says, "Your Highness, I have grave news. The mathematician will deplete the royal treasury. On the 41st day alone, we would have to give 1 million bags of rice, because 2 to the 40th is 1 right here. So we've got 1 million grains of rice. So we've got 1 million bags of rice, which is more than the entirety of the treasury has in rice. And if we kept going, if we let it run all the way to the 64th day, we would have to send him more rice than the total that the world has ever produced, because we'd be at 2 to the 63rd, which would come out to be 9 trillion bags of grains. Sorry, 9 trillion bags of rice. Look, we have ones here, we have thousands here, we have millions here, billions here, trillions here, quadrillions here. It would be 9 quintillion grains of rice. If we knock off these first ones, we see that we're still at 9 trillion bags of rice. That's a lot of rice, and the world doesn't have that much by a long shot. So, the mathematician's greed has enraged the king, and the king immediately orders all shipments of rice stopped. The mathematician is not getting any more rice, and the mathematician is to be executed. Now, the mathematician, being a clever fellow, he hears the soldiers coming on the road, and he escapes. He fled the kingdom with the few bags of rice that he could manage to carry on his back, and he had to find a new place to live far, far away from the kingdom. So the moral of the story is twofold. First, don't be overly greedy, don't try to trick kings, but more importantly than that, exponential functions grow really, really large in a short period of time. They get big fast. Even if they start at a seemingly very, very small, minuscule amount, they will grow massive if given enough time. So that's the real takeaway here from this story. Exponential functions get big. They can start off small, but given some time, they get really, really big. All right, let's see an application to this stuff. When you put money in a bank, they will usually give you interest on your money. For example, if you had an annual interest rate of 10%, annual just means yearly. So a yearly interest rate of 10% on a $100 principal investment, the amount that you put in the bank, the following year you would have that $100 still, they don't take it away from you, plus $100 times 10%. Now 10% is a decimal, is 0.10, so $100 times 0.10, so you'd get that $100 you originally started with, and you would have $10 in interest. Great. But you could leave that interest in the account, and then your interest would also gain interest. The interest is going to get interest on top of it, so we would say that the interest is compounded because we're putting one thing on top of the other. So you've got $110 in your bank account now, right? Because you had $110 total at the end last time. So $110 gets hit by that 10% again, so you've still got the $110, plus now $110, 10% of $110 is $11. So notice that $11 is bigger than 10. $11, your interest is growing. Over time, you're getting more and more interest as you keep letting it stay in there. So you continue to gain larger and larger amounts of each interest. Compound interest is a common and excellent way to invest money because over time your interest gains interest and gains interest and gains interest, and eventually it can manage to get large enough to be even larger than the principal investment and be the thing that's really earning you money, is the time that you've spent, the time that you've let it compound. We can describe the amount of money, amount of money, in such an account with an exponential function. A of t equals p times the quantity 1 plus r over n to the n times t. Let's unpack that. So p is the principal. P is the principal in the account, the amount that is originally placed in the account. So in our example that we just had, that'd be $100 put in, so our principal would be 100 in that last example. R is the annual rate of interest, and we give that as a decimal. So here's our R right up here. So in the last one, that was 10%, so it was expressed as 0.10. N is the number of times a year that the interest compounds. So N is the number of times that we see compounding. So N equals 1 would be yearly, N equals 4 would be quarterly, N equals 12 would be monthly, N equals 365 would be daily. So in our last one, it compounded annually every year, so it compounded just once a year, so n was equal to 1. Notice that n also shows up here. So it's n times t. And then finally, t is just the number of years that we've gone through, so it is times t. So let's understand why this is the case. Well, if we looked at 10% just on the $100, we'd have $100 times 1 plus 10%, right? So $100 times 1.1 equals $110. Now, if we wanted to have this multiple times, well, the next time, $110 times 1.1 again, we'd get another number out of it. And then if we wanted to keep hitting it, so we can just think of it as 100 to the 1.1 to the t. And that will just give us the amount of times that the interest has hit over and over and over. So our principal times the 1, because the bank lets you keep what you started with, plus the interest in decimal form, all raised to the t, the number of times, the number of years that have elapsed. Now, what about that divide by n part? Well, let's say that we compounded it twice a year. So they didn't just give you your interest in a lump sum at the end of the year, they gave it to you in bits and pieces. So the first time it compounds, if they did it twice a year, let's say they did it semi-annually, 2 times a year, then it'd be 1, because they let you keep the amount of money, plus 0.1 over 2, because they're going to do it twice in a year. So the first time in the year, we'd get 100 times 1 plus 0.05, 100 times 1.05. The first time the year it gets hit, so you'd get $105 out of that. Now, They could do it again, and we could have $105 get hit with another one of 1.05, and then we could calculate that again, and that'd be the total of the amount that you'd have over the year. Now notice, 105 times 1.05 is going to be a little bit extra because we're getting that 5 times 1.05 in addition to what we would have wound up having. We would have 105 times 1.05, 5.25, so we'll wind up getting 5.25 out of this, so we'll have a total of $110. $110.25. So by compounding twice in a year, we wind up getting 25 cents more than we did by compounding just once in a year. So the more times we compound, we get more chances to earn interest on interest on interest. So 1 plus 0.1 divided by 2, now it's going to happen twice in a year, so since it happens twice in a year, we have to have the number of times that's happening in the year times the number of years. So at the twice in a year scale, we'd see 1.05 to the 2 times number of years because it happens twice every year. And this method continues the whole time, so that's why we've got the divide by n, because the rate has to be split up that many times, but then it also has to get multiplied that many times extra because it happens that many times extra in the year. So that's where we see this whole thing coming from. Now, we noticed over the course of doing that the more times it compounded, the better, right? We earn more interest if it's calculated more often, right? The more often our account compounds, the more interest we earn because we have more chances to earn interest on top of interest. So we'd prefer if it compounded as often as possible, right? Every minute, every second, every instant, if we had it happening continuously, absolutely constantly. This idea of having it happen more and more often leads to the idea of the natural base, which we denote with the letter e. The number e comes from evaluating 1 plus 1 over n to the n as n approaches infinity, as this becomes larger and larger. Because remember, the structure last time was 1 plus this rate divided by n to the n times t. So if we forget about the times of the year that it's occurring and forget about the rate, we get just down to 1 plus 1 over n to the n. So we can see what happens as n goes out to infinity. What number does this become? It does stabilize to a number, as you can see from this graph here. So by the time it's gotten to 40, it starts to look pretty darn stable, right? It's got this asymptote that it's approaching. So it started to become pretty stable. We can look at some numbers as we plug in various values of n. At 1, we get 2. At 10, we've got 2.594, 100, we've got 2.705, 1,000, 2.717, 10,000, 2.718, 100,000, still at 2.718, and there's other decimals there, but we see that it winds up stabilizing, right? As we put more and more decimal digits, as n becomes larger and larger and larger, we see more and more decimal digits that e is going towards. E is stabilizing to a single value, and we see more and more of its digits every time we keep going with this decimal expansion. So as we continue this pattern, e stabilizes to a single number. Now, it doesn't stabilize to a single number where we finished figuring it. We keep finding new decimals, but we see that the decimals we've found so far aren't going to change. E is 2.718281,828, and that decimal expansion will keep going forever. Just like pi, the number e is an irrational number. Its decimal expansion continues forever, never repeating. So that decimal expansion just keeps going forever. Just like pi isn't 3.14, it's 3.141, right? It just keeps going forever and ever and ever. So e is the same thing, where we can find many of the decimals, but we can't find all of the decimals because it goes on infinitely long. Now also, just like pi, the number e is deeply connected to some fundamental things in math and the nature of the universe. E is connected to the very fabric of the way the universe and just things work. So pi is fundamentally connected to how circles work, and circles show up a lot in nature and the universe. So pi is connected to circles, and e is connected to things that are continuously growing, things that are always growing, that don't take this break between growth spurts, but that are just always, always, always growing. So e gives us things that are doing this continual growth. E has this deep connection, and if you continue on in math, you'll see e a lot. Also, if you continue on in science. One application of e is to see how an account would grow if it was being compounded every single instant. That idea that we're not just doing it every year, not just every day, not just every minute, not just every second, but every single instant. And that gives us p, our principal amount, times e to the rt. The amount in our account is p times e to the RT. We can also just remember this as PERT. PERT is the mnemonic for remembering this. P is the principal, or we can just think of it as the starting amount, however much we started with. R is the annual rate of interest, and it can even be used for things that aren't just annual rates, but R is the annual rate of interest, and remember we give that as a decimal. If we give it as a percent, things won't wind up working out. And T is the number of years elapsed. Now this above equation, this one right here, this PERT thing, this can be used for a wide variety of things that grow or decay continuously, things that are constantly growing or constantly decaying. You'll see it show up a lot in math and science as you go further and further into it. It's very, very important, this idea of some principal amount times e to the rate times the amount of time elapsed. So you can use it for a lot of things, and while we'll wind up in these next few examples be using some other things than just e to the RT, with the exception of the examples that involve continuously compounded interest, you can actually bend a lot of stuff that you have in exponents into using e. So it's easiest to wind up just remembering this one and then changing how you base your r around it. Now, don't get too confused about that right now. We'll see it more as we get into other things in logarithms, and also just as you get further and further into math, you'll see how this really, p times e to the RT, is really a fundamental thing that gives us all of this stuff that's doing growth. Finally, exponential decay. So far, we've only seen exponential functions that grow as we go forward. F of x equals a to the x, where our base, a, is greater than 1, so it gets bigger and bigger as we march forward. But we can also see decay if we look at 0 is less than a, which is less than 1. If a is between 0 and 1, it's a fraction, it's smaller than 1. So here's some examples. If we have 4/5 x, we see that one in red. 1/2 x, we see that one in blue. 1/10 to the x, we see that one in green. So notice how quickly the functions become very small as they repeatedly lose value because of the fraction compounding on them. Right? 1/10 becomes very small. By the time it's gotten to just 2, we've got 1 over 10 squared, which is equal to 1 over 100. So it becomes very, very small. By the time we're at 1 over 10 to the 10th, we're tiny, absolutely tiny. Once again, looks like it touches the x-axis, but that's just because it's a picture. It never actually quite gets there. There's always a thin sliver of numbers between it, but it gets very, very, very close. So they'll all become very, very small as the fraction on fraction on fraction, as they compound over and over, bits get eaten away each time the fraction hits, so it gets smaller and smaller and smaller. But notice, if we go the other direction, we wind up getting very large. Just like normal exponential functions that grow, where a was greater than 1, they got small when they went negative, they grew when they went positive, because when they went negative, they flipped. We have that same idea of flipping. If we have 1 over 10 to the -2, well, that's going to be 10 over 1 squared, which is equal to 100. And that's why we see it blow up so quickly. It becomes very, very large as we go negative for decay things. But we'll normally be looking at it as we go forward in time, which is why we talk about it decay and things that are greater than 1 being growth, because we're normally looking as we go forward, as we go to the right on our horizontal axis. All right, let's look at some examples. A bank account is opened with a principal of $5,000. The account has an interest rate of 4.5%, compounded semi-annually, just twice a year. How much money is in the account after 20 years? So what do we need? We go back, we figure out the function we're using. Our formula is that the one for interest compounded, so it's our principal times 1 plus the rate, but divided by the number of times it occurs, and then also raised to the number of times it occurs in the year times the number of years that pass. So what are the numbers we're dealing with here? We've got a principal of $5,000. We have a percentage rate of 4.5%, but we need that in decimal, so we've got 0.045. And what is the amount of time? The amount of time is 20 years. So if we do this with it going semi-annually, twice a year, we look at that, it'll be n equals 2. So a at 20 equals, what's our principal? $5,000 times 1 plus the rate, 0.045, divided by the number of times it occurs in the year. It occurred twice, right? N equals 2. So divide by 2. Raise it to the 2 times how many years? 20 years. We go through that with a calculator. It comes out to $12,000, $175.94. Now, what if we wanted to compound more often? What if it had been compounded quarterly? or monthly, or daily, or continuously. So if it was compounded quarterly, it would occur 4 times in the year, right? Every quarter of the year, every season, so n equals 4. So we have 5,000 times 1 plus 0.045 divided by 4. That'll be 4 times 20. We use a calculator to figure this out. It comes out to $12,236.37. So notice that we wind up making a reasonable amount more than we did when it was compounded just twice in the year. We're making about $50 more, a little bit more than $50. What if we have it do it monthly? How many months are there in a year? There are 12 months in a year, so there'll be n equals 12. 5,000, our initial principal, times 1 plus our rate over 12. Kind of losing room. 12 to the t, 12 times t. So what's our t? Our t was 20. Sorry about that. 12 times 20. That'll come out to be $12,277.33. What if we've got it at daily? How many days are there in the year? There are 365 days in a year, so that'll be an n of 365. So at 365, we've got 5,000 times 1 plus 0.045 over 365, number of times it occurs, 365, number of times it occurs in the year. We had 20 years total. We simplify that out. We get $12,297.33. And what if we managed to do it every single instant we actually had it compounding continuously? Well, if n is equal to infinity, we're no longer using this formula here. We change away from this formula and we switch to the PERT formula, because that's what we do for compounded continuously. So that's going to be 5,000 times e. What's our rate? 0.045. How many years? 20 years. Once again, we punch that into a calculator. There will be an e key on the calculator. You don't have to worry about memorizing that number that we saw earlier, because there's always an e key. 5,000 times e to the 0. Let's just get a number here, so there's not much. We're not going to wind up doing this numbers because they'd be hard to do, so we'll use a calculator. So let's just hop right to our answer. We'd get $12,298.02. Finally, I'd like to point out, so notice that we wound up seeing reasonable amounts of growth when we jumped from going only semi-annually twice a year to 4 times a year. And we also saw an appreciable amount of increase when we went from 4 times a year to 12 times a year, right? When we went to monthly, we got a jump of a little over $40. When we managed to make up to daily, we got a jump of about $20. But going from daily to every single instant forever only got us $1. So we get better returns the more often it happens, but they wind up just sort of eventually coming to an asymptote. It increases asymptotically to this horizontal, it eventually stabilizes at a single value. So you won't see much difference between an account that compounds every single day and account that compounds every single instant. There won't be a whole lot of difference. So it's way better to have daily versus yearly, but daily versus continuously, not really that noticeable. Second example. Day a child is born, a trust fund is opened. The fund has an interest rate of 6% and is compounded continuously. It is opened with a principal of $14,000. What is the fund worth on the child's 18th birthday? So what formula we'll be using? We'll be using PERT. The amount that we have in the end is equal to the principal we started with times e to the rate that we're at times t. What's our principal? Our principal is $14,000. What is our rate? Our rate was 6%. We can't just use it as a 6. We have to change it to a decimal form because 6% says divide by 100, so we get 0.06. Finally, what's the amount of time that we've got? Our first one, we're looking at a time of 18th birthday, so 18 years, t equals 18. So a principal of $14,000 times e to our rate 0.06 times the amount of years, 18 years. We plug that into a calculator, and we see that on his 18th birthday, the child has managed to get $41,225.51. So, pretty good, right? But what if the child managed to not need the money, didn't really want the money, wanted to save it, maybe use it to buy a house when he was 30, put down a good down payment on a house when he was 30. So at that point, if he was 30 before he took out the money, the child would have 14,000, same setup, but we're going to have a different number of years, times 30. That would wind up coming out to 84,000. It's more than doubled since he was 18. Pretty darn good. So more than doubled. He's managed to make $84,000 there. That's not bad. You could get a good down payment on a house with that, so pretty useful. But what if he didn't really need the money? If he managed to not spend that money and he was like, I'll use it as a retirement fund. That way I won't have to invest for my retirement at all. I've already got it set up. How much would he wind up having at the age of 65? We've got 14,000. Same setup as before, times e to our rate, 0.06, times our new number of years we're doing is 65 years, and he would manage to have a whopping $691,634.29. So this points out just how powerful compound interest was. We managed to start at $14,000, but if we can avoid touching that money, if we can just leave it for a very long time, we can get to very large values as the interest compounds on itself over and over again. In 65 years, which is a very long time, but in 65 years we managed to grow from $14,000 to $691,634. It's a lot of money, right? And this gives us an appreciation for how important it is to make investments for retirement at an early age. It's difficult when you're young, but if you manage to invest when you're young, if you can hold off on spending that money now, it can grow to very large amounts by the time you want to spend it to retire. So that's the benefit of investing early, being able to do that. Also, it shows just how useful an interest rate is. If that 6% was bumped up to 8% or 10%, we'd see massive increases. You can get a lot of increase if you can just get that percentage rate up another point or two. Pretty impressive. All right, third example, population of yeast cells doubles every 14 hours. If the population starts with 100 cells, how many cells will there be left in 2 weeks? So this isn't compound interest, and it isn't continual growth like we had before, so we might want to build our own here. The population is doubling. So let's say n is the number of cells after some time. We'll set it up as a function. Makes sense. We're in exponential function land right now. So n of t is equal to, well, how many cells did we start with? We started out with 100 cells, and we were told that it doubles. So we're going to have some times 2, because we multiply by 2. How often does it do that? It does it every 14 hours. So if we have our number of hours, so t equals number of hours, t divided by 14 will be how many times it's managed to double, right? After 14 hours, we've multiplied by twice once. After 28 hours, we've multiplied by doubling twice, right? We've got 2 times 2 at 28 hours. So let's do a quick check and make sure this is working out so far. So if we had n at 14 hours, we'd have 100 times 2 to the 14 over 14, which would simplify to 100 times 2 to the 1. So we'd get 200. So that part checks out. And let's try one more just to be sure. At n of 28, if we had double, then we know that we should be at 400, so we can see what's coming there. So 2 times 28 over 14, that simplifies to 100 times 2 to the 2, which is equal to 100 times 4, or 400. So that checks out as well. So it passes muster. This makes sense as a way of looking at things. So as long as we have the amount of time we've spent and the number of hours, then we can see how many cells we've got after that number of hours. Now, we were told to figure out how many will there be in 2 weeks. And we can assume that none of the cells die off, so the number just keeps increasing. So it's a question of how many times has the population gotten to double. So if that's the case, what number are we plugging in? It's n of how many hours? Is it 2? No, it is not 2. Well, how many weeks? Oh, 14 days? No, it's not 14. What were we setting this up in? T was set up in number of hours. So the question is, how many hours do we have on hand? So let's first see how many hours is 2 weeks. Well, 2 weeks, how many days is that? Well, that's going to be 2 times how many days in a week? 7. So that's 2 times 7 days. How many hours is that? 2 times 7 times 24, or 14 times 24 hours, which we could then figure out with a calculator and get a number of hours. But we can actually just leave it like that, which we'll see in just a few moments is a useful thing to do. We notice, hey, there's a divide by 14 coming up. Maybe it'd be useful to just leave it as 14 times 24, a little less work for us. So 14 times 24, and now notice 14 times 24, that is the number of hours in 2 weeks. So that's why we're plugging that in, because once again, the function we built, our n of t function that we built, was based on hours going into it. So we can't use any other time format. 100 times 2 to the 14 times 24 is the number for t, divided by 14. Hey, look at that. The 14s cancel out. We can be a little bit lazier. That's nice. 100 times 2 to the 24. We plug that into a calculator, and we get a whopping 1,677,721,600 cells. That's more than 1.5 billion cells, right? Ones, thousands, millions, billions. So we're at 1.6 billion cells. Well, actually closer to 1.7 billion cells. So this gives us a sense of just how fast small populations are able to grow. And that's how populations grow. They grow exponentially because each cell splits in half. So if we have one cell split in half to 2, and then each of those splits in half to 4, and each of those splits in half to 8, this is going to do this process of exponentiation. We're doing this through doubling, so we're going to see very, very fast growth. And we actually see this in the real world. We could also write this for ease as we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the same thing. We could write it as 1.67, approximately 1.67 times 10 to the 9th cells, so that we can encapsulate that information without having to write all of those digits. So that's scientific notation for us. All right. Fourth example, final example, the radioactive isotope uranium-237 has a half-life of 6.75 days. Now what's half-life? We'd have to go figure that out. Luckily they gave it to us right here. Half-life is the time it takes for 1/2 of the isotope, 1/2 of the material of our isotope, to decay and break down, to go through a process of decay. If you start with 1 kilogram of U-237, how much will have not decayed after a year? So we're saying after 6.75 days, we will have half a kilogram, right? We start with 1 kilogram, and we know after every 6.75 days, we will have lost half of our starting material. So we will be down from 1 kilogram to half a kilogram that has not decayed. So let's see if we can figure out a way to turn this into another function. So let's make it amount. The amount of our isotope that is not decayed based on time is equal to, how much did we start with? We started with 1 kilogram times what happens every cycle? 1/2. We half it every time we hit it on a cycle. So we have every time we hit on a cycle. So how fast is a cycle? Number of days, we'll make t into the number of days, because we see that we're dealing with days based here. So t divided by 6.75. So let's do a real quick check. So we check because we know after 6.75 days, we should have 1/2 a kilogram. So let's check that by plugging it in. A of 6.75 is going to be 1 times 1/2 raised to the 6.75 over 6.75, which is the same thing as just 1/2 to the 1, which equals 1/2. So sure enough, it checks out. Seems like the way we've set this up, seems like it passes muster, because it's going to divide by half every time the 6.75. So if we plugged in double 6.75, it would divide by half twice, because it'd be 1/2 squared. So seems to make sense. We've set it up well. And we can see that this also can we just write as 1/2 times, well, let's just leave it as it is. It gives us a better idea of how this works in general for half-life breakdowns. So now we're going to ask ourselves, how long? What is the time that we're dealing with? In our case, t is 1 year. What is 1 year in days? Because we set up our units as days, because that's what our half-life was given to us in. So 1 year is 365 days. So at the end of that, when you plug in 365 equals 1, the amount that we started with, times the half-life will occur every 6.75 days, and we're having 365 days go in. We plug that all into a calculator, and we get the amazing number, amazingly tiny number of 5.273 times 10 to the negative 17th kilograms. Really, really, really small number. To appreciate how small that is, let's try to expand it a bit more. So kilograms is 1,000 grams. Sorry, 1 kilogram is 1,000 grams. So that means that a kilogram is 10 to the third grams. So we could also write this as 5.273 times 10. If it's 1,000 grams for a kilogram, then that means we're going to get to increase by 3 in our scientific exponent. So scientific notation, we're now at 5.273 times 10 to the negative 14th grams of our material, which if we wanted to write this whole thing out, we would be able to write it as 0.00000, 5 so far, 0, 0, 0, 0, 0, 10 so far, 0, 0, 0, 13. And let's see why that's the case. We can stop writing there. Because if we were to bring that 10 to the negative 7, taken to the negative 14th here, and remember, it's in grams because we had grams here, because that would count as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, because we can move the decimal places 14 times to the right by having 10 to the negative 14th, and that's how that scientific notation there is working. Or alternatively, we could also write this with kilograms as the incredibly tiny 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 5.273 kilograms. And if we counted that one out as well, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we've got that 5.273 times 10 to the negative 17th kilograms there as well. So it's much easier to write it with scientific notation. That's also probably what a calculator would spit out because it's hard to write a number like this long on a calculator. So we're much more likely to get it to see it in scientific notation. So 5.273 times 10 to the negative 17th kilograms, which is absolutely minuscule amount of radioactive material left considering that we started at 1 kilogram. So that shows us how decay works. All right, cool. We've got a pretty good base in exponential functions. Next, we'll see logarithms and see how logarithms allow us to flip this idea of exponentiation. And then in a little while, we'll see how logarithms and exponential functions, how we can sort of oppose the two against each other. Pretty cool. We can find out a lot of stuff with this. All right, we'll see you at educator.com later. Bye.